Hi, I'm an electrical and mechanical engineer. I made a special Stewart's platform stabilization robot to impress my professor and get my master's degree. This video will just contain the technical details behind its creation and the problems that I faced. If you want more information on what's at stake, feel free to watch my last video, but it's not required to watch this one. The next video will contain clips of the robot in motion and completing some demos, such as moving to commanded poses, stabilizing items on top of the platform as it's moved up and down in Z, rolling a ball from one point on the platform to another, and others like that. You can think of my robot as a fork of Jugglebot if you know what that is. I'm calling mine StableBot. A lot has happened since the last video, and it's going to take a lot of explaining. So this video will be separated into 5 parts. 1, the physical construction. 2, the wiring and electrical engineering behind it. 3, the communications and technical architecture. 4, the changes I had to make after the April 21st demo. And 5, everything I did wrong. Firstly, the physical construction. The base plate is made out of 1/2 inch thick aluminum plate and is 3 feet in diameter. The aluminum base alone weighs around 75 pounds. This weight is important to reduce vibrations and ensure it is completely stiff. And the reason it's not a single plate of metal across the bottom is frankly because it was cheaper that way, but that introduced a new problem. I had to somehow put the plates together. The options were weld them together, use some kind of epoxy to put them together with some dowels maybe, or to drill holes and use more plates to bolt them together. I was worried about the heat distortion with welding, and the university doesn't have a welder powerful enough for 1/2 inch thick aluminum anyway, so plates and bolts it is. And I decided to use 1/4 inch thick stainless steel plates and 10mm shoulder bolts to attach the plates together. But the locations of the holes had to be exact to make sure the plates all come together properly. So I had the poster printing service at the university print out a 1:1 scale drawing of the base plate with markings on where the holes were to be placed. I then used spray adhesive to make sure that the paper didn't move while I used a center hole punch to mark where to drill all of the holes. This was a slow and tedious process, which resulted in my only 10mm drill bit exploding. Turns out stainless steel is really hard. Who knew? The legs are made from 1 inch diameter aluminum rods to support the weight of this platform without risking them breaking off. And moving this thing for the first time was a huge pain in the butt. So I added these handles for easier transport, along with adding a lot of other attachment points where those handles can be easily moved to. Let's get into the linear actuators now. Each leg is constructed from 3D prints and carbon fiber tubes. The carbon fiber tubes were cut with an abrasive cutting blade on my portable bandsaw, clamped with V-blocks, and the links were set with a set of homemade cutting fences made from 2040 aluminum extrusion. And they were measured with this absolutely giant set of calipers. And yes, Mom, I made sure to wear a respirator when cutting the carbon fiber. The 3D prints were printed on campus at the Marston Student Library. The prints alone cost over $400, and they were frankly pretty low quality. I definitely need a good 3D printer, and heat set inserts were used whenever possible to provide a sturdier interface than just plastic threads. The linear actuators are mostly the design of Harrison Lowe, with some changes made by me to increase rigidity and to make full use of my 3D modeling computer. Each actuator uses around 3 meters of Dyneema thread routed along 6 different pulleys to control the extension and retraction. I've only had to redo 3 of them. They're connected to the base plate with these medical magnetic ball joints, which allow for a really great range of motion. And the top platform is attached with these shaft support brackets and a lot of hot glue. And the top platform is 3.5mm thick carbon fiber cut with a carbide compression bit on my router. Next is the electrical design. In this section, you'll notice that I use a lot of O-Drive and Xsense parts, but that isn't just because they sponsor me, but because they really are the best option for my use case. I reached out to them to sponsor me, not the other way around. Every robot starts with power. The power supply is a Meanwell 48 volt 600 watt. This connects to my emergency stop button, which I also use as an on-off switch. The power then goes into the OGen-Regen clamp to dissipate the brake current whenever the motors are braking. Brake current is redirected into these 2 huge 4-ohm power resistors put in parallel, resulting in around 500 watts of power dissipation at 2 ohms. The power is then routed to my terminal blocks, which then provide power to everything else down the line. The motors are O-drive 150 kV BLDC motors. The 150 is how many RPM per volt they're rated at. They are controlled with the O-drive pros using the absolute RS-485 encoders to close the control loop. The communication to all of the O-drive pros are done via CAN cables. The first and last O-drive pro are set to 120 ohm to mark the start and end of the CAN bus, and they are all run at the default 1 MHz refresh rate. The CAN signal is powered with a Castle Creations BEC Pro set to 12 volts using the Castle link. The CAN signal is then converted to a USB signal using the O-drive USB to CAN adapter. The USB signal is then isolated with the O-drive USB isolator, and the signal is finally then plugged into my Raspberry Pi 5. Well, more accurately, the spot pair USB hub for my Raspberry Pi 5. The reason I picked this hub is because it allowed for easy expansion into other USB devices and allowed for me to power the Pi using 5.1 volt power supply with ferrule connections. Yep, that means another Castle Creations BEC Pro, but this one is set to 5.1 volts output, and to reduce ripples further, I added a Castle Creations capacitor pack to help smooth any of those ripples in the power supply due to the motors. Something I haven't mentioned yet but is absolutely essential is to ensure that everything has a common ground. So to avoid ground loops, I use these Vago 3-terminal levers attached to these Vago DIN rail blocks, which were mounted to the DIN rails on the bottom platform. The BEC's USB to CAN adapter, regen clamp, and capacitor pack were also all mounted to these DIN rail mounting brackets with zip ties. And last but not least are the Xsense MTI 360 IMUs, which were bolted to the bottom platform and top platform, and are communicating over UART to USB directly to the Raspberry Pi 5. And thankfully, they have a pretty good ROS driver. Another note is that almost all of the cable was 12-gauge copper wire terminated with ferrules for better electrical connection and ease of disassembly and reassembly. And all of these electrical plans will be uploaded to my GitHub if you want to make something similar. Part 3. The Communications and Technical Architecture. As I mentioned previously, the drives are connected to the Pi using CAN to USB, and the IMUs are connected to the Pi over UART. The Pi is running a slightly modified kernel of Ubuntu 24.04 and ROS2 Kilted Kaiju. All of the drives are calibrated one by one with the O-Drive WebGUI to flash firmware 0.6.11-1, but the newest firmware allows for calibration and node ID setting via CAN, which didn't exist at the time. And all controls are sent from my custom WebGUI, which is accessible if the Pi and the controlling computer are connected to the same Wi-Fi network. The stabilization controls are just a PI with some other helpful gains to improve dead zone. There are ROS topics for basically everything that moves data through the robot, and they sort of split into 4 groups. The status coming up from the hardware, the commands going down from the browser, the IMU streams, and the vision pipeline. For the hardware telemetry, my main control node publishes the leg encoders and leg currents at 20 Hz, so I can see where every motor is and how much current it's pulling. The platform roll, pitch, and yaw are also published at 20 Hz for displaying in the WebGUI. Same with the status at 2 Hz, which is just a JSON blob of armed flags, IMU freshness, level errors, O-drive errors, and routine state. The Xsense MTI 630 IMUs publish at 400 Hz each. Only the platform one is actually being used in the control loop right now. The base IMU is reserved for wave rejection that I'll get into in a future video. For commands going the other direction, instead of using ROS services, I made one big JSON action bus that the browser publishes to and the control node replies on. Every button in the GUI just becomes a JSON message on the control commands node. I did it this way instead of the services because ROS Bridge has a intermittent discovery bug with services, and I got really tired of restarting the daemon. The whole thing gets glued to the browser by a ROS Bridge on WebSocket plus a small Python HTTP server that serves the single file Tailwind and ROSlib.js GUI. Part 4. April 21st and beyond. At the time of the demo on April 21st, the robot was able to stabilize within 0.1 degrees in both pitch and yaw, move the legs to any commanded positions or tilts, move the platform up and down in Z while maintaining this stabilization, and run orbit demos with no ball. After displaying these capabilities, Dr. Islam was disappointed that the robot was unable to detect where a ball was when placed on top of the platform. This makes all of the demos just open loop control, so he gave me a task. Between April 21st and May 1st, I had to implement a complete vision system to detect where the ball was and use its position to do closed-loop control of this ball. I quickly ordered a 6-foot-long, 1-inch diameter aluminum rod to mount the camera and lighting systems to, a lot of small ring mounting equipment, and the small ring 40C RGB lighting system, and the Luxonis Oak D Pro camera. The Oak D Pro has stereo vision, an IR depth sensor, a monochrome camera, and a normal RGB camera. It also has a Intel Movidius Myriad X vision processing unit, which allows for me to run image recognition models directly on camera to reduce latency. Before I could even start on ball sensing, I had to increase the accuracy of the inverse kinematics of the platform, which required the creation of a Rosbag analysis method to better fit the actual relationships between the motor turns to how the platform moves in pitch and roll. This dataset would end up being a few gigabytes in size and took multiple hours to capture, but it was worth it. I was now able to control the platform down to 0.05 degree resolution. Next was figuring out the rotation and translation matrices between the camera and the center of the top platform so ball movement can be translated to the top platform reference frame. To make this process possible, I printed out and carefully stuck matte vinyl stickers to the top of the platform printed with a known pattern of Uruko markers with specific IDs to allow for a faster and more consistent calibration than trying to rely on the depth sensor alone, as that method is unable to discern rotation. Finally, with this improved inverse kinematics and known rotation and translation matrices, I could begin on ball detection. The simple method is color thresholding using CV2, but the amount of time it takes to process each image results in a ball position publishing rate of only a little over 10 Hz, which is significant latency compared to when the image was taken to be analyzed. Every other method that required for the image to be sent to the Raspberry Pi for processing would also result in similar issues. The last tool I had at my disposal was the visual processing unit inside of the camera itself. I spent a night manually labeling images with the help of RoboFlow to train custom YOLO V6N and YOLO V8 image recognition models to identify the ball, my hands, and the Uruko markers. I then wrote and ran a series of benchmarks that proved YOLO V8's increased accuracy was worth its slower 30 Hz speeds compared to YOLO V6N. And only then I could finally get to actually controlling the ball, not just finding it. It started with a traditional PID controller before adding on a ramped movement starter, which gradually increases the angle of the platform until it is able to break the static friction between the ball and the vinyl sticker on top platform. And this coefficient of static friction and its breakaway angle were measured with another calibration Rosbag method and used to set the ramped movement starter angle values. And the goal of this demo was to move the ball from its current position to any other specified position on the platform. Sadly, it was unable to keep the ball from overshooting and falling off. After doing an analysis of command timings, latency, ball position, and actual platform tilts, it was clear that the issue was that the positions to control the ball were reached only after the ball had already moved too far away from its position to be effective. To account for this, I implemented a look-forward algorithm that used the ball's current position and previous position delta time ago and used that to create a velocity vector to better guess where the ball will be instead of sending a tilt command for now. The controls send a tilt command for where the ball will be based on the measured latency of the system. This is where I am now, and this latency compensation has greatly improved accuracy. The next step is to do another Rosbag calibration to move from simple linear velocity estimations, which result in orbital patterns, to a full simulation based on the actual behavior of the ball. Next video I release will have this new velocity simulation method implemented and will be full of some great demo videos. If you're here for what actually worked, feel free to click off the video now. But if you want to hear about the problems and the countless failures, stick around. Finally, Section 5, Problems and Fails. This section will be divided into 3 mini chapters. First, what failed mechanically. Second, what failed electrically. And third, what failed software-wise. And this is just a greatest hits. Assume that almost everything that could have gone wrong did go wrong at least once. And starting with the mechanical fails. I learned to always buy 2 of every drill bit. I've had a few explode into my legs while drilling into the stainless steel. Next, I don't have a centering vise, which made drilling holes in the ends of rods a terrible experience. Next, I never had enough clamps at any point in the project. Buying double of what you think you need is the only way to have half as many as you actually need. And it turns out making a robot wider than the door frame I have was pretty stupid. I had to disassemble and reassemble the robot every time I had to move it. And when cutting the carbon fiber with my router, I should have used more protection than just a respirator. My arms felt the stabs of the fibered needles in them for weeks. The 0.48mm Dyneema thread that I used for the linear actuators was far too thin. Every single time one snapped, it was hours of time lost rerouting the thread through the tiny pulleys. Next, into the electrical fails. Thankfully, there was only 2 electrical fails, but one of them almost killed over $3,000 worth of robot parts. When I was testing the actuators by connecting them to my power supply sitting on my desk, I did so with positive on the left and negative on the right. And when I mounted the power supply to the robot, I mounted it upside down to the bottom of the base platform. When turning on the robot for the first time, there was a puff of smoke and a flash of light before I could hit the e-stop. I had sent 600 watts of reverse polarity directly into the O-drive regen clamp, which resulted in its diodes failing short and burning up. At first, I thought that the current could have destroyed all of the drives, but thankfully only the regen clamp was destroyed. And on the recommendation of Solomon from the O-drive crew, I used a screwdriver and chiseled the failed diodes off the board. And somehow that worked, and it is still in use now. Thankfully, the only other electrical problem I had was the Oak D Pro camera. It pulled too much power for the Raspberry Pi to handle. And a USB-C splitter and data splitter combined with a wall-powered USB-C charger was the only way to keep the camera from crashing the Pi. And finally, into the worst part, software fails. This is just the highlights. Again, assume that almost everything that could have gone wrong did go wrong at least once. And the biggest fail by far was my inverse kinematics. I had a perfectly clean geometric IK that I derived on paper to convert commanded platform pose into motor turns. The problem was it was rotated by somewhere between 45 and 62 degrees per leg compared to what the platform was actually doing physically. The mean magnitude error was 130% on roll and 450% on pitch. I spent days tuning PID gains on top of this broken inverse kinematics before I figured out what was going on. And tuning gains on top of a broken IK is as useful as underwater fire safety. Next, the Uruko markers on top of the platform and the IMU body frame disagreed by about 155 degrees because the IMU is just bolted on at that rotation. I wasted nearly a full day on PID gain tuning before realizing that issue. Next, the pitch and roll signs are not symmetric in the rotation math. Right-hand rule around Y plus for positive pitch actually sends the plus X edge of the platform down, which means that the ball slides towards plus X. And so I always learn to derive sign conventions from the rotation matrices instead. Then there was the issue where my main set pose function and my level loop were each using a different inverse kinematics path. One was the geometric IK, the other was the empirical Jacobian I had fit from the Ross bag. So commands going through one path were silently rotated 55 degrees from commands going through the other. This one line of code cost me half a day of troubleshooting. And on the vision side, I spent an entire morning trying to figure out why the camera was only giving me 4 hertz of ball detection when I had set it to 60. I checked the USB negotiation, frame pool sizes, ISP scaling, depth AI, all of it. Turns out, set FPS is a ceiling, not a floor. Auto exposure was picking 30 to 67 millisecond integration times, and the frame rate just floor divided. So switching to set manual exposure and plugging in an actual light source took me from 4 Hz to 30 Hz with the exact same code. Next, I spent an entire day building an auto tuner. Bayesian optimization, hill climbing, the whole deal. 27 trials, 0 improvements whatsoever. The problem was that the auto tuner placed the target ball position randomly each trial, and the fitness noise from a random target distance was larger than the actual signal from changing the gains. So hand tuning while sorting bag digests in a comparison script ended up beating my own auto tuner by an order of magnitude. The stiction breakaway logic was its own special hell. The ball sits on a vinyl sticker with a coefficient of static friction of 0.037, which means the platform has to tilt around 2.14 degrees before the ball will roll at all. So I had a stiction relief routine that would slam the platform to max tilt to break stiction. Problem is, slamming to max tilt gives the ball way more energy than the controller can damp. So every time the ball broke loose, it would shoot into an orbital limit cycle around the platform. I replaced it with a slow ramp that starts just below the breakaway angle and creeps up. So this way the ball breaks loose at a lower velocity. Then there's the, did I actually deploy that class of bug? My vision package and my control package are two completely separate ROS packages. And if I forgot to include the vision package in my colcon build command, the install tree would just not reflect my source change. I lost multiple 4-hour debug rounds running source code that was just not actually the right source code. Same deal with the systemd services. I have one service for the launch file and one for the GUI server. And if I edited the GUI and forgot to restart the GUI service, the browser was happily talking to the previous version. I now have a single deploy script that always rebuilds all 3 packages and restarts both services. No exceptions. The O drives have a really fun bug class where every parameter the control loop depends on has to be both persisted in Flash via the configurator and reasserted at runtime on every level on. Neither alone is enough. So the Flash gets overwritten by recalibration, runtime gets reset by disarm, velocity feed forward, current limits, control mode, all of them silently revert to factory defaults whenever the web GUI runs its configuration script. So I now set the velocity limit at 3 independent layers: the firmware, the Python CAN code, and the GUI sliders. On the ROS bridge side, I tried switching from JSON to CBOR RAW for image transport, thinking it would cut my bandwidth in half. And turns out, on Pi 5 with ROS2 kilted, ROS bridge just does not work with CBOR RAW whatsoever. And those were just a taste of the failures I had. And if you made it this far, thanks for sticking around. The next video will have the new velocity simulation rolling ball demo working, and hopefully a few less fails. Then after that, I might make a video about the tools used in the making of this robot and which ones I would buy if I have to do it again. Thanks for watching.